For COS 350, Data Structures and Algorithms at the University of Maine, one of the projects that we had to work on was if given a set of points on a 2D plane, it should produce an output of triangles connecting these points together. That is, non-overlapping triangles. The method that I used was Incremental Delaunay Triangulation. The basic idea of how my implementation works is when a new point is added, it finds the triangle that that point should be inserted into. It then splits the triangle into the necessary number of triangles. Like if it's an internal point, it splits it into 3 new triangles with the new point in the middle. It then queues up the edges to check to make sure that the Delaunay triangulation property holds, and if it doesn't, it would flip the edges to to optimize the triangulation. The Delaunay triangulation property is that there are no circumcircles of any triangles which should contain the any points of any of the other triangles inside of them. So if you notice, like these 2 triangles here, the circumcircle around this triangle on the right, going through these three vertices, those that circle contains a point on this other triangle. And then you can see the opposite also true. In this left triangle, there's a point of a right triangle inside this circumcircle. So that means that this edge here between these 2 triangles needs to be flipped or rotated. So instead of being vertical, it's going to rotate to be horizontal, causing a new configuration of triangles. One of the properties of these new triangles is if you see the circumcircle of the top triangle and the circumcircle of the bottom triangle, you notice that there are no vertices of any of the other triangles inside of it. That produces a very nice, very clean triangulation that basically it prevents as many long skinny triangles as possible. They can still have long skinny triangles if it's, like here on the perimeter, or if that's just the circumstances of how it is. But in general, the triangles are going to be very nicely shaped, and it's going to be an overall good triangulation. The way that my algorithm finds which triangle to place a new point inside is that the whole thing starts with a super triangle that surrounds everything. Those points will later at the triangulation phase, be kind of like removed, only leaving the internal triangles behind. So this triangle here, these triangles are the triangles we want for our triangulation, but the algorithm starts with a very large triangle first, which is going to be subdivided, for the triangulation, and then those surrounding triangles get removed. So it starts with the super triangle, and then to find the point, let's say that a new vertex was going to be inserted, well, let's say here, like in this bottom triangle, this blue here. First it checks what, each time it checks which triangle it is in. So it's in this triangle, and it goes to this side. Let's say it checks it's in this triangle, and then it's in this triangle, and it finds it's in this triangle. This might not be the best way of doing it. It's the way that I did it, but one problem is I currently have a bug where if a vertex is perfectly on an edge, because it cannot split the triangles into three, because if you have three collinear points, you cannot make a circumcircle around it because it would have, those points are in a line. You need to have a triangle. So it causes problems, and the right way would be to split the triangles into, because it's on the edge, it has to split two triangles instead of just one triangle, and it should have each one be two separate triangles. So there's 4 new triangles instead of 3 new triangles, and everything needs to be connected together. So if I was going to redo this, I think much of the algorithm we simplified in this bug could be avoided using a quad tree data structure, where the triangulation, the steps, for reaching the triangulation are not used, but instead bounding rectangles surrounding the triangles could be used. And it could actually possibly speed up things, because calculating if a point is inside a triangle could be a little bit could be a little bit slow in general. Well, I still might need to check that, if because you'd want a tighter fit than just a rectangle. So, but anyhow, it would simplify that problem I was talking about, where triangles need to be split in a way where there's a new vertex on the edge. But anyhow, so it finds the triangle that it's in. The point is added to that triangle. So let's say it's added to this triangle here, where my cursor is. It would split this into 3 triangles. The surrounding edges would be added to a queue to be checked to see if they need to be rotated with the surrounding triangles. And it's just like each time they gets updated, the edges, the new edges of these rotations get added to the queue until nothing more needs to be rotated and the queue is empty. So I'm gonna add this here, and I don't know if you easily seen that, but this edge used to be going this way, but after it's added, now is rotated this way. So in general, this works pretty well, as long as there are no collinear points. Like for example, I don't have it here, but I tested it with grid, and that kind of causes a mess, because a grid has a lot of collinear points. But in future implementations, if I was going to re-implement it, I'd do it like I said with the quad tree data structure. So, that's the basics of how this implementation of the incremental Delaunay triangulation was done. You first find the triangle you need to insert a new point into, and then you check edges and flip them as needed. The triangle representation that I used was, the points are in counterclockwise order, and the edges, the opposite edges, have the same numbering as the opposite vertex. So if this is vertex 0, this is edge 0. If this is vertex 1, this would be edge 1. If this is vertex 2, this is edge 2. And it keeps track of the neighbor, the triangles on each side of the edges. This was a little while ago, but I think that's the basic of how I had that set up. I'd have to refresh my memory about some of the exact details. So this is my implementation of the incremental Delaunay triangulation. Sorry if my explanation might not have been the best, but you know, it's the basic idea of how it works. So it's incremental Delaunay triangulation.